So if, in particular, if the transformation is ergodic, then f given I is actually the set of all constant functions, and so that says that mu n dot f converges to constant functions, and that constant is then the integral of f d mu. So these are exact analogues. Now they require some work, not all that much work, because I stated all the theorems yesterday in terms of maximal operators, and then you need to prove maximal theorems for the mu n's. And that follows reasonably straightforwardly from the Fellner condition, and again I've written out the details in my notes, or you can find them in a lot of places around the place. And there is a maximal ergodic theorem. I guess I'll write that. So it's quite easy actually to see how to generalize these basic ergodic theorems to So I'd like to talk about unique ergodicity and transitivity. So if let's dip for a moment into the dangerous world of continuous ergodic systems rather than measurable ergodic systems. I'd like to make a little comment about what happens there. So the question is, can you find a measure on this metric space which is invariant under G? And for amenable groups, sorry? Yes, I probably want to say ergodic. I'm about to give a condition which makes sure it's ergodic all the time. So, I think it's the same. Well, if it's a transitive system, it's the same. That's what I'm about to say. So I probably shouldn't have defined this until I had talked about transitive systems. It should act transitively on the measure space, and then I don't have to say ergodic in the measure. So. Let's take a continuous function, then mu n dot f is continuous. And the theorem is called Krylov-Bogoliubov. So if the action is transitive, that means you can get from, there's a dense orbit, then in fact there is a unique G invariant measure, and that measure is ergodic. No, I think it works for amenable groups. Oh, is the space compact? Yeah, maybe you've got me compact metric space. Otherwise, you could have R acting on R itself, and that would be a counterexample, I think. Right, so now I'm going to talk about entropy, which was the main topic for today, and I got halfway through my lecture without starting it. Chapter 2 was rather short. So remember, we defined metric isomorphism. I won't write up the definition. So there was a problem in the 1930s, 40s about, is the shift on 2 elements, can it be isomorphic to the shift on 3 elements? And nobody could actually resolve that. They couldn't show that whether or not there was an isomorphism between one and the other. And this was resolved with Rocklin and Sinai's definition of entropy, and that enables one to distinguish between those 2 shifts. And then later, Ornstein came and proved this great theorem, which says that if they're Bernoulli systems, which I'll define in a little while, then entropy is actually a complete invariant. Bernoulli systems of the same entropy are, in fact, metrically isomorphic. So I'd like to, my aim now is to tell you about that theorem in the case of Z, and then secondly to tell you how it generalizes to amenable groups. And how do you do it? Well, you try to make a skyscraper construction inside the group, and that gives you a set of coordinates, and you try to then compare those coordinates. That in a nutshell is what I'm going to talk about for the next little bit. So let's talk about partitions for a bit. Not such a inflammatory word in India as it was in about 1950, but sorry, that was a very bad joke, wasn't it? I remember the British partitioned India, didn't they? They divided into 2 bits, and so a partition is you take your space X and you A partition P is a set of sets P1, P2, up to Pn, disjoint, whose union is X. And the entropy of a partition and I guess we can take log is usually log base 2 actually for these things, but if you change to a different logarithm base, you just multiply by a constant here. So this is the so if you take a step function on the partition where you associate to each element of the partition log of the measure of the partition, then that's called the information function. And you can see if you integrate that, then you get the entropy. There are interpretations of entropy. I very much like the way B.V. Rao wrote it in his lecture notes, where you think you have an infinite word and you only know it up to a certain finite amount, and the question is how quickly is that finite word approaching the infinite word, and the answer is it's approaching at a speed of e to the minus h times the n, sort of n, so that h is the constant in the exponential approach of the full information by these partial bits of information. Anyway, this doesn't concern us as pure mathematicians. We are interested in, this is an interesting invariant, I think. Or maybe it does concern us, actually. It should concern us. Let's supposing we have a sub-sigma algebra of B we have the conditional entropy and conditional information function I of P conditioned on C x is equal to minus the sum of P in P chi Px log of, and then you take the conditional so you take instead of mu of P, you take the conditional function of characteristic function of P conditioned on C, and H P given C is the integral of that. So that's the entropy of a partition. I haven't mentioned a transformation yet. So let's supposing we have a transformation on x b mu t, bimeasurable, etc., etc. Then so you take the successive images of the partition P under T, and then you use them to generate a sigma algebra. So this is the join of the sigma algebras. So, for example, you start with this, you partition it like that, then you apply T to it. T will maybe send this set to there, and perhaps those two sets to there, and then you take all the possible intersections of one of these guys and one of those guys, so then you'll get more different sets, and that gives you a larger sigma algebra. And let's keep doing that out to infinity and take the lim sup over this over n, dividing it by n. And the entropy of, so that's the entropy of T with respect to P, and the entropy of then you take the supremum over all those entropies, supremum over all finite partitions. And that's called the entropy of the transformation. Well, there are lots of nice properties of information functions and entropies, probably which many of you know. I'm not going to write up everything, but for example, I of P1, the join of P1 and P2, condition on C at X is equal to the I of P1 conditioned on C, X plus I of P2 conditioned on A1 join C, X, where A1 is the sigma algebra generated by P1. So that's a nice property of the information function, which then leads to thank you. So there are many properties of this kind which were proved by Sinai when he started investigating it, and which and Shannon and people like that, they're important in information theory as well. And in fact, So you can take T, take its images, and then you can generate a sigma algebra. In fact, that lim sup over there is a limit. So there are, this is probably, that function is convex, and therefore you can, it's a really nice, it's called Feketa's theorem, that if you have a convex theorem, then you divide by n, then there is a limit there. So you can show that that lim sup actually is a limit. So a major, if you continue to develop these properties of entropy, which I'm not going to be able to do too much of, then you can prove inequalities like this, that the information of P, function of P1 given C is always bounded, dominated by the information of P2 given C. And so, and H of T given P1 is less than or equal to H of T on P2. And it follows xb mu t is a factor of y c nu s, then h of t is less than or equal to h of s. And also I need some more chalk. And so sorry? No, his theorem was probably one of the... So therefore it follows that if I can work out the entropy of the 2-shift and the entropy of the 3-shift and show that they're different, then they're non-isomorphic. But how do I work out the entropy of shifts? Well, the answer is given by Sinai's theorem, which no, I haven't defined factors. So that means that, let's see, x is a factor of y means y equals x cross z, where z is some other space. So I've made a little bit of a leap of judgment here, and I haven't. You then can show from this that. What if I? Sorry? Yes. And so in here you can take a well, all right, that's another way of saying it, yeah. Yeah, so you could restrict T to the sub-sigma algebra C. That's another way of writing this. So what does Sinai's theorem say? Well, it says if there's a generating partition, actually, I'll write it properly. I mean, some of this is true not only for invertible transformations as well, so I'm stating a slightly so actually the entropy, this supremum here is actually achieved by taking a partition which generates the sigma algebra. That was what Sinai's theorem was. And so we can now that then gives you enough to calculate the entropy of the shift. So let xn be 0, 1 up to k minus 1, say. Oh, maybe I'll write L minus 1 because I've been using k for other things. So I'm going to take a finite space like this and define a probability measure on it by putting weights on these different, no, it's confusing to have it like that. And